All right, so I want to give you a look at the example at the beginning of the first programming assignment. There's been a lot of questions about this example. Some questions that I realized that weren't described very well in written form on the programming assignment. And so I just want to work through this example a little bit with you in this video and see what's really going on here. Okay, so the first thing is that we need to declare these symbolic function variables. Now, declaring is something that if you have a lot of experience with programming, is something that you're really useful. If you don't have a lot of experience, it's just really just telling the programming language that we want these variables to be of a certain type. And so here we've declared 3 functions that we are going to use. One is y, one is z, and one is f. Now, putting the x in parentheses like that does 2 things. It declares x as a symbolic variable as well, and it makes x the independent variable for y, z, and f, which are then dependent variables. Why do I always say the wrong thing? Okay. So now when we use y, z, and f in future lines, then MATLAB knows that these are going to be symbolic variables. Okay, and that means that we can set z of x equal to tangent, and that works out all right, and we can take the derivative, we can integrate it, and we can do all sorts of fun stuff. All right, now to get to the next part, this is the part where people start having questions. So if I want to, let's say I want f of x to be the solution of the differential equation f prime equals f. This is what I'm going to type in. Now let's break this apart a little bit. Right here, this is the differential equation. Okay. And actually I messed up because I need a double equals there. This is the differential equation right here. The reason we need a double equals is because that's actually what equals. That's how we write equals in MATLAB. If you have a single equals, that's used for assigning things to a variable. So here we have f of x is our symbolic variable that we declared up here in our top line, and by writing a single equals here, whatever comes out of this differential equation solver, that's the dsolve function. It's used to solve differential equations. Here's the differential equation that we're solving, and now whatever comes out of this ends up right here. Now the differential equation right here, we needed f to be a symbolic variable for dsolve to recognize this as a differential equation. If you try to use a different function name that you haven't declared as a differential equation, a symbolic variable with an independent variable associated with it, in this case that's x, then dsolve can't recognize this as a differential equation. There are other things that you can input into dsolve. For example, there are ways that you can write a differential equation as a string instead, and tell it what you want the independent variable, but I kind of like this way. I don't know why. So let's see, when we hit enter here, what do we get? Well, it tells me that now f of x equals the function c4 times the exponential of x. Now, of course, the differential equation f prime equals f, we know has c e to the x as the general solution. And so c4 here, that is our arbitrary constant. This is something that's a little bit curious to me that I don't fully understand. I don't know why it uses 4, why it just jumps straight to 4. I know that if you solve a differential equation with with order 2, so maybe let's see, I can redeclare f of x as a blank symbolic variable, and now I can write f of x equals d solve. Let's do the second derivative of f, and the way that I do that is going to be a diff of f comma 2, and then I want this to equal f. Now let's see. Okay, so now I have an arbitrary linear combination of e to the x and e to the negative x, and it makes sense that these are two different numbers here, because that's telling us that these are two different arbitrary constants. Why they skip to 5 and 6, I don't know, and that's the part that's kind of mysterious to me. And what really stinks about this is that when you're doing the homework and you're entering in the homework, you need this to be the same arbitrary constant label as the solution that I have on there. Otherwise, it'll tell you that it's wrong, even if it's right. And that means that you need to enter in your even though there's different ways that you can set up your differential equation within dsolve. If you do it a different way than I did, then you will end up with even if you have the right answer, it'll be an arbitrary constant with a different number next to it, and it'll count that as wrong. And that makes me sad, and I don't really know how to get around it for these general solutions. Now, this won't matter when we do the next thing, which is to use dsolve to solve a initial value problem. So now I can enter in the same differential equation, but I can put my initial value, which is going, in this case, we're going to set y of 0 equal to -3. Okay, so now we don't have any arbitrary constants, and you guys know all about this because it's an initial value problem. There's a unique solution. We know what that constant is, and in this case, it has to be -3. Okay, now the next part of this example is all about building a directional field for this differential equation. Now, the first thing that we need for a directional field is we need a grid. And if you look at the next line in the example, it's going to be something like this. 0.5 to 5. Okay, now let me talk a little bit about what this means. Let's just run it first. Okay, now mesh grid creates two different matrices, and when on the left-hand side here, when we set it up like this means we're assigning the first matrix of mesh grid to XP and the second one to YP. So let's actually take a look, and I could do a couple things. I could write XP here and hit enter. I can also go over here to my workspace and click on XP, and this can show me exactly what the values of XP are. So you can see that XP is a 21 by 21 matrix, and every column is every entry in a single column is the same as all the others. The reason for this is XP is going to be the X values from -5 to 5 with increment 0.5. So, on the far left, I have X value of -5, and then I go up to -4.5, and then -4, and so on. So these are all x values. And when I think about the open rectangle, -5 to 5, -5 to 5. But as you move up and down in the y direction, the x value needs to stay the same. And so that's why the columns here are all identical, because the x values are all identical within each column, and that makes sense. Now, if we were to go and look at yp instead, we also have a 21 by 21, but now the points are all y values, and it is interesting that that the top values are -5 and the bottom values are 5, and that's just how MATLAB does these things. But we're not going to have to account for that with anything later. And so when you pair these two matrices together, xp and yp, pair each corresponding entry, and you have an x value and a y value for one point where you want to make an arrow for your directional field. And now, how can we make that arrow? Well, if you recall, the second day of class, and I was introducing directional fields to you, and I put all the slopes on the board, and then I wanted to add arrows to each of the slopes. And I had forgotten how to do it. I was a little bit rusty on this. And the thing is that we want to break up. Here, let me close. I don't need this anymore. We want to break up the differential equation a little bit here. And so let me just write out for you our differential equation. So we have, this is what we're working with. The derivative of y equals y. And so because of that, we know the slope at each point in the directional field. It is just equal to the y value, so that's not too hard. But what directions do the arrows go? And to have some meaning with arrows, what we have to do is break this up into two different functions. Diff y is really like dy over dx equals y. So here's how I want you to think about this. We're going to come up with two functions. One is dy and one is dx. And they can be in terms of y or x. Each of them can have a y or x in it, doesn't matter. And we want this to be in such a way so that dy divided by dx equals whatever we want diff of y to equal. So in this case, the differential equation tells us that it equals y, and that means that I want dy to just be equal to y and dx to be equal to 1. As long as these two functions that I'm dividing are continuous in my domain that I'm worried about, then MATLAB isn't going to have any trouble creating the directional field. So that's why we do this. We set dy equal to yp, all right? Because yp is the y values, and dx is going to be equal to 1's 21. So the whole point of this, 1's creates a matrix where every value is 1. And I want that dx function to be equal to 1 everywhere in the grid. And because my grid, if you look over at xp and yp, because they're 21 by 21, I want a 21 by 21 matrix with all 1's in it, and that's going to be dx. Now, if I take the entries of dy, divide by the corresponding entries of dx, I'll get the y value at each point, which is what I want from the differential equation. All right. Now, when you can't just copy this stuff over when you're doing the actual exercises as part of this assignment, because if you do, then you'll be working with the wrong differential equation. What we want is to find two functions, one for dy, one for dx, that when you divide by dy dx, you get everything on the right side of the differential equation after solving for dy dx. And you want these functions to be continuous on the domain in question. So now that we have all that, then we can just do, we can use this quiver command to plot a directional field. And the first two inputs that we need here just need to be the x and y coordinates. And now we need the arrows themselves, and so we're going to put dx and dy. And now when I do this, I get this glorious directional field, and I don't know if you can actually see this. Yeah, it doesn't look like you can, so let me add a new source. Okay, and we're going to do, there we go. Okay, so now you can see this beautiful directional field, and that's exactly what we wanted, right? And except I also want to be able to plot my function y on here as well. Now, if I want to put another overlay one graph on top of another one, I need this hold command. So I'm going to write hold on, and now anything in between here is going to plot that same plot on the same graph as before. So I'm going to plot my function y. That's the same y that we came up with back here. Yeah, it's just this guy. And I want to match the same x and y range so that it doesn't like mess up anything on the graph. And that's actually why we're using EasyPlot. It makes inputting your x and y range really easily, makes it really easy, because now it's just going to have x between -5 and 5 and y between -5 and 5, and then I can write hold off. So now you can see that the graph has this curve added to it. And what's really cool, and what I really kind of want you to take away from this assignment, is that when you plot a solution to a differential equation on top of a directional field, that function is going to follow the arrows, and you can see how it follows the arrows perfectly here. Solutions to differential equations are functions that follow all the arrows on a directional field. And if you have something that follows the arrows that isn't a function, then we write that as an integral curve. Let's see, I guess the one last thing that I want to bring up here is that in the assignment you're asked to do this on a different grid. Here we had a grid where both x and y go from -5 to 5 with an increment of 0.5. This won't work for the assignment itself, because we want I think we want x from 0 to 5 and y from -5 to 5. And so I'll let you figure out how to do that. Of course, it's something that you can look up online without too much trouble. So yeah, good luck with finishing off the assignment, and hopefully this video was helpful, and I will see you later.